All right, let's start sharing our screen. And let me go over here. Let me go back to, again, make sure if you haven't yet done so to do the chapter 13 test by the end of the day on Saturday. I'll try to get them all graded on Sunday. The chapter 14 test will be due the following Monday. The final exam will be due the following Wednesday. Hopefully you get a little bit more time in between. So the final exam is going to be made up of questions taken off the back tests. I'm still tweaking the final exam, so I can't tell you exactly how long it is. Part of me wants to see how far we get in this chapter 14. I have to apologize. A whole bunch of you submitted your homework and activities, and I really appreciate that. I believe that I got all of the homeworks graded, but I haven't quite gotten all of the activities graded because I think you don't know how much I appreciate the effort that you guys put into all of these assignments. So many people are submitting for me so many pages of work, and I hope I usually try to turn around and get everything graded by the very next day, but with grading online, I feel like I can't give everything the appropriate attention if I rush through it. And so I apologize that they aren't all graded yet, but realize that it's because I see all of the work that you're doing and I'm looking at everything you submit. I know some of you have been having problems submitting things into Blackboard. And if you do so, please email me your stuff. If I can't open what's in Blackboard, I'll send you an email asking you for the email. And the reason that I appreciate the Blackboard submissions over the email is because in Blackboard, I can write on them as if I were actually physically grading papers. And then you can look at what I graded and see what you got right or wrong. Before we get started, does anybody have questions on any questions, any of the old homework, any of the new homework, any of the projects? And again, remember, we're not doing the chapter 14 projects.
On the homework, I did have a couple questions.
On the new homework?
Yeah.
Okay. Let me go over here, and I didn't quite open the textbook yet because I wasn't sure if we'd be looking at chapter 14 or 13. So chapter 14 textbook, where did you want to look? First, second, third, or fourth page?
Page 729.
Okay.
Number 31.
Okay. Oh, I'm sorry, my internet is slow today. It's doing something. It's doing something. Or not. Let me get the physical textbook and read the problem from there. I do not have, oh, there it is. Okay. As soon as I give up, it'll come in. All right, I am going to go through and cut and paste this question into the notes. So it says, in one unfortunate shipment, 10% of the MP3 players manufactured by Imperfect Electronics had defective switches, 5% had defective batteries, and 2% had both defective. If you purchase an MP3 player in this shipment, what's the probability that it has a defective switch or a defective battery? A good switch but a defective battery, that's both a good switch and a good battery. I want to, if you don't mind, this is where we left off last class and what we're getting to. We had said last class that to find the probability of A or B is equal to the probability of A plus the probability of B minus the probability that both occurs. Do you remember ending last class with that statement? So if I go back to this question, the probability that it's the switch or the battery is equal to the probability that it's the switch plus the probability that it's the battery minus the probability that it's both. And so the probability that it's the switch is 10%. The probability that it's the battery is 5%. And the probability that it's both is 2%. And so that gives me 0.13. Does that make sense?
Yes.
Okay. Then I'm going to skip back to the notes for a second, where we're, after we do another example with or, we're going to get to this idea of complementary events. And complementary events are two subsets, two events that have nothing in common. Complementary events are two events that have nothing in common, but they make up the entire sample space when they combine. So they have nothing in common, but they make up the entire sample space. And what we're going to find that if A, and it's using that same notation for a complement that we had with sets in Math 108. A bar is the complement of A. Well, if together they add up the entire sample space, what happens is the sum of their probabilities is 1. So we would be able to say that the probability of A plus the probability of its complement will equal 1. And so we'll get that the probability of an event is equal to 1 minus the probability of its complement. So what does all of that mean? If I go back up here, if the probability that has defective switch is 0.10, the probability that it has a good switch, not defective, would be 1 minus 0.10 or 0.9. Does it make sense that 90% of the time we would have a good switch if it's thank you, the switch is not defective. So likewise, then what's the probability that it has a good switch but not a defective, but a defective battery? Well, let's see, that there's 5% defective batteries. Of those 5%, 2 of them had both. And so we take that 5% defective and subtract the 2% where both were defective, and that would give me 3% where just the battery was defective. Does that make sense?
Yes.
And then C, using this idea of complements, if I want both to be good, well, there's a 13% chance that one or the other is bad. The probability that both is good would be 1 minus that 13%. The probability that something's bad, which would give me 0.87 or 87%. Does that make sense?
Yes.
Okay, and so actually the reason you had a question on that was we were in the middle of developing those concepts last class, and that's where we're going to pick up from now.
I just don't understand like word problems when it comes to like percentages and like the way that they word them. So I just struggle through them.
Well, feel free to ask. Does it make sense here reading it? 10% had bad switches, 5% had bad batteries, 2% had both. That's what you really need to, take away from the wording. Okay.
Yeah. I just didn't see like where it said good, so I was like really confused.
Yeah. A good switch means not defective. Okay,
Okay.
great. Did anybody want to look at anything else from any of the other homework questions before we pick up from where we left off? No, go ahead. Okay, not hearing any concerns then. We had left off with that idea of or, and in an ideal world, we would have done that with the experimental probability with results of everybody in class, rolling the dice, but obviously we couldn't because we're not in person, and I'm not creative enough to think of a way to get around that. I apologize. I'd like to do another example with theoretical probability deck of cards for picking one. And so by the probability of J, let me try to make this font just a little bit bigger for you. Is that a little easier to read? I mean, the probability of a jack. And how familiar are you folks with a deck of cards? How many jacks are in a deck of cards? Everybody right? There's a jack of hearts, diamonds, clubs, and
4.
spades. So there's 4 out of my entire deck is 52. And if you reduce, you'll find that 4 goes into 52 13 times. For the probability of a heart, well, for the heart, we have 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, king, queen, ace. So that counts up to 13 out of the 52 cards, which would reduce to 1/4. If I want the probability of the jack of hearts, is everybody all right? There's only one card, that's the jack of hearts. There's only one card that's both a jack and a heart at the same time. So that would be one of the 52. So we need all of those pieces over here to find the probability that it's a jack or a heart. We accept when we see that word or, we'll take the probability of the first, the jack, plus the probability of the second, the heart. And then we have to subtract the probability that we get both at the same time. So the jack, I'm going to use the not reduced form, 4 out of 52. The hearts, I'll use the not reduced form, 13 out of 52. But both happening at the same time is that 1 out of 52. What we're saying is one of these 4 jacks is a heart. One of these 13 hearts is a jack. And so that card's being counted twice. So we need to subtract that probability out. Now we've got common denominators, so we'll keep that denominator. And when I add the numerators, 4 plus 13 is 17, less 1 is 16. And that'll reduce by a factor of 4, giving me my final answer to be 4/13. And so in probability, and also we'll find a little bit later in counting, when you see that word or, it's the probability of the first plus the probability of the second, but we don't want anything to count twice. And so we have to subtract the probability of both occurring at the same time. Does that make sense to everybody?
Yes.
Great. Then next place we're going is that idea that we talked about with, well, if there's a 13% chance that I get something broken, what's the percent chance that nothing is broken? It would be 1 minus that. That idea of complementary events, events that have nothing in common, but combined they make up the entire sample space. So we're saying that the probability of an event occurring is 1 minus the probability of its complement, or the probability of it not occurring. The probability of a success is 1 minus the probability of the failure. And with that question, like what's the probability of having nothing broken, being 1 minus the probability of something broken, we're going to find that it gives us a shortcut for some problems. So I'd like to look at an example involving dice. I'm asked, what's the probability of getting a sum of at least 3 on the roll of 2 dice? Well, at least 3 would mean 3 or higher. So that could be 3 or 4 or 5, all the way up to 12. And so as I look at my sample space for 2 die that I took the liberty to reinsert in the notes here, could be 3 or 4 or anything higher. You notice the only thing that we're excluding is the sum of 2. So we can say that the probability that I get 3 or higher, the complement of that is getting a sum of 2. So that's going to equal 1 minus the probability that I get a sum of 2. And that sum of 2 is one of the 36 outcomes. And so again, if I think of getting a common denominator and writing that 1 is 36 over 36, whoops, that's supposed to be a minus, not equal. Minus that 1 out of the 36, this probability would be 35 out of 36. And so sometimes, if the probability that you're looking for seems complicated, it's easier to think of taking the complement of that event. Instead of finding the probability that something does happen, sometimes it's easier to find the probability that it doesn't happen and subtract from 1.
Are you getting the 36 because when you multiply 6 times 6, it equals 36?
And I'm also looking at this diagram that we had discussed last class. All of the possible outcomes when I roll 2 die, if I were to count them all up, there are 36 outcomes. Yes, but it also comes from that 6 times 6. Okay,
Okay.
so that over here, this diagram shows me that there are 36 total outcomes. So besides complementary events, we sometimes talk about independent events. And two events are independent if the occurrence of one does not affect the occurrence of the other. What happens in one event has no influence on what happens in another event. An example might be if I toss a coin twice. When I toss the coin the first time, I might get a head or a tail. When I toss the coin the second time, I might get a head or a tail. Did the result of the first toss have anything at all to do with the result of the second?
Oh.
No, they're independent. Another example might be if I toss a coin and roll a die. What happens on my coin is not at all affected by what happens on my die. And so over here, it's written for experimental probability. It will be true for all probability, whether experimental or theoretical. The probability of A and B will always equal the probability of A times the probability of B. So, and that happens if the events are independent. So let's say, for example, I toss a coin twice. What's the probability? Both are heads. Well, we already clarified that those two are independent events. The probability that the first one is a head is a half. The probability that the second one is a head is a half. And so that the probability that I would get two heads would be about 1/4 of the time. And from this, what I'm hoping you're getting is that if I see with that word and, I'm just going to multiply those two probabilities, but only if the events are independent. And so sometimes we use simulation to approximate. We use one event to estimate the probabilities of another for all sorts of reasons. A lot of times it's even ethical. So let's say that I want to find out the experimental probability that a family with 3 kids has 1 boy. Well, if I were to go ahead and do that, I could ask all of you in class to go out, have 3 children, report back to me in a few years, and tell me how many kids you have, boys or girls. Would that be a real good way of doing that experiment? I don't think so. I don't think it's ethical for me to go and ask you guys to all go have 3 children. But now, wait a minute. If I look at having a child, my sample space is either a boy or a girl. And while those two probabilities aren't exactly equal, they're pretty gosh darn close. Well, what's something else that we have with 2 outcomes that's much easier to do? Couldn't I say I could toss a coin? And on my coin, I have heads and tails. And so rather than asking each of you to go out and have 3 children, couldn't I instead ask each of you to toss a coin 3 times? And we could let's say, the head represent having a boy, the tail represent having a girl, and we could simulate it by everybody tossing 3 coins and counting how many people got just 1 head on those 3 tosses. And so that's the general idea of simulation. Does that make sense to everybody? And again, if we were in the classroom, I would have given everybody 3 pennies and asked them to toss them, and we'd count how many people got exactly 1 head on their 3 tosses. Are you guys all right if we just stop this discussion here? Because I don't know if you guys all hit the penny to toss 3 times.
Yes.
At one point in time when I was getting my master's degree, I got took a course on computational modeling, which is this same idea, where instead of using having kids use something like tossing a coin to model it, and it involved an awful lot idea of computer simulation. And a lot of times when you're looking at computer simulation for something, it's done in that same vein. So that, for example, if they're doing a simulation of traffic and you come to an intersection, they use random number generators to represent, if it's a 1, the car goes straight, if it's 2, it goes left, if it's a 3, it goes right. And the idea of using some other thing to simulate that physical event. So there's a lot of work has been done into the idea of simulation, but I think this example of tossing a coin to see if a child is a boy or girl is something that's like a good introduction to the idea of simulation to explain to kids. Okay, so all right, besides that idea of simulation, you're going to find in some of the homework there's a geometric model. And again, if we were doing the activities, we would be doing a lot of this spinner type of thing. I could give everybody a spinner and ask them what the probability that the arrow would fall in region A. And so what do you think the probability that if I spun this, my arrow would fall in region A?
2/4.
Region A would be 2/4 or a half. What would be the probability that it would fall in region B?
1/4.
What would be the probability that it would fall in region C?
1/4.
1/4. And does it make sense with this geometric model, this physical thing that we have in front of me? Wouldn't the probability be the ratio of the area that we want over the total area? Or the idea that the probability that it lands in A is a half because A takes up half of the spinner. The probability that B is a quarter is because B takes up a quarter of the spinner, and so on. And I have to apologize, I can't remember if it's a question from your textbook or the contemporary math textbook. Something like this you might look at if you have a dartboard and you want to find what's the probability of falling in a given region. What you would end up doing is you'd find the area of the region. And for the probability, you divide it by the total area of the board. And so that would be the probability that I'd land in that region. And I think to a certain extent this geometric representation for probability is pretty straightforward. We've spent a bit of time earlier in the semester looking at all of those area formulas. So it doesn't make sense that the probability that you would, like with a dart, land in a given area would be the ratio of that area to the whole thing. The next thing that we talk about is conditional probability. And this is more involved with events that might not be independent. With one type of conditional probability experiment, what we're doing is we're limiting the sample space to the given condition. And I know in the textbook they present this as a formula, which you can use. It involves union and intersection of the different sets. I think it's more direct to look at it, the idea of limiting that sample space. And so if we look at this example that I pulled out of the textbook, it says that all the 24 students in Mr. Henry's preschool are either 3 or 4-year-olds, as shown in the table. Well, it's the table below. A student is selected at random. So over here, for the first question, what's the probability that the student is 3 years old? Well, that would be the number of 3-year-olders over the number in the class. And so if I look at the table, we know that this column adds to 14, this column adds to 10. So the total in the class, as we were told before, is 24. And the number of 3-year-olds would be 14 out of the 24. Does that part make sense to everybody? Now, this next one says, what's the probability that the student is 3-year-old, given that the boy was selected? And so over here, this is what we mean by putting a condition on it. Because our condition is that the boy was selected, this time we're restricting our sample space to just boys. And so this time, if I'm restricting my sample space to just boys, I'm only using this part of the table. And so here, the probability that I have a 3-year-old, given it's a boy, means that I'm only looking at the number of boys. So we're looking at the total of the boys, and the top would be the number of 3-year-old boys. Oh, Lord. I apologize. I'm thinking and talking and writing at the same time, which leads me to misspell in silly ways. So 3-year-old boys is 8 out of the total number of 3-year-olders is 11. And so that would be 8 over 11. I want to add a part C here because this part C sometimes leads to confusion. Part B says, what's the probability that we had a 3-year-old given it was a boy? C, I want to ask, what's the probability that the student is a boy given they were 3 years old? The first, B says, what's the probability that the student is 3 given it was a boy? This one asks, what's the probability that it's a boy given they're 3? And with this one, do you see here our condition is 3-year-olds. And so this time we're restricting our sample space to just those kids that are 3. And so here, the condition of being 3 years old means that we've only got 14 students that we're looking at, the 3-year-olds. Of those 3-year-olds, just like up here, we said there were 8 3-year-old boys. Well, there are 8 boys that are 3. So this probability is 8 out of 14. And I know some people, if you read too quickly, read those two things as asking the same question. Notice with this, the order of the words does matter. What's given is what we restrict our sample space to. So the given is what we restrict our sample space to. And if I could spell restrict, it would be a good thing. R-E-S-T-R-I-C-T, the sample space to the given condition. And does that make sense to everybody, the difference between those two situations? Any questions?
No.
Then the next thing that I'd like to do, I'm going to answer this question that's down below about a probability tree. But I'm going to insert a separate page in here because in your textbook, they talk about 2 different types of tree diagrams. First type of tree diagram is a possibility tree. And it just shows the possible outcomes. The second one is a probability tree. And it labels each outcome with its probability. And let's start looking at a possibility tree for if I toss 3 coins. I'm going to start at a dot. And what I'm going to show first will represent the first coin. And is everybody all right? The first coin can either be a head or a tail. Then off of that, I'm going to show the second coin. If the first coin is a head, the second coin can be either a head or a tail. And likewise, if the first coin is a tail, the second coin can either be a head or a tail. Then the next row of branches coming off would be my third coin. And it doesn't matter what happened on any of the preceding tosses, that third coin, no matter what happened before, can either be a head or a tail. And so this is a possibility tree. It shows all of the possible outcomes. Using that on the preceding page, I wanted to know that the probability that I get 3 heads. Well, to find the probability that I get 3 heads, I'm going to look at this diagram and see which of the pathways give me 3 heads. And so here, this is the only pathway where they're all heads. Every other pathway has at least 1 tail. So there's one way of getting 3 heads. And then I'm going to count 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes. And so the probability that I get 3 heads would be one of the 8 outcomes. How is that possibility tree diagram for everybody?
Good.
Then for a probability tree with this one, I would draw the same thing. First coin is a head or a tail, but with a probability tree, I'll label that each of those happens half the time. And then the second coin is either a head or a tail, and each of those happens half the time. And here, again, each is a head or a tail. Each of those would happen half the time. This one's not too exciting in terms of a probability tree because each of those are equally likely. Here, with a tree diagram drawn like this, if I want the probability that I get 3 heads, well, that's still the only pathway for 3 heads. And what I would do is I'd take the 1/2 times the 1/2 times the 1/2, take the product of those probabilities to get my 1/8. That all right?
Yes.
I think the difference between the two types of tree diagrams is a little bit clearer with the next example that we're going to look at. It says a bag contains 3 white and 5 black marbles. I want to pick 2 without replacement. Let's find the probability that we get 1 of each color. But here I'm not replacing them. Oh, actually, yeah. Okay. So first, let's look at the probability tree first. Probability tree, I can get either a white or a black. The chances of getting a white is 3 out of 8. The chances of getting a black is 5 out of 8. So far, so good.
Yes.
Now, the second one can be either a white or a black. But because I did not replace it, there's only 7 left. If the first one was a white, 2 of the 7 that remain would be white. If the first one was a white, 5 of the 7 that remain would be black.
Wouldn't it be 4 of the 7?
No, because we're going on the assumption over here that we picked a white one. You're on the other side. If the first one we picked was black, then there's 4 out of 7 black left. But if the first one that I picked was black, there's 3 out of 7 white left.
So why doesn't the bottom for the black stay the same then if it's on the left side?
Because we still picked 1 marble.
Oh, okay.
Okay. So to get 1 of each color, it could be a white and a black, which would be 3/8 times, 5/7, or it could be a black and a white. That should be B, which would be 5/8 times 3/7. And so when I add them, I have 15 over 56 plus 15 over 56, which would give me 30 out of 56. Instead, if I wanted to look at a possibility tree, this is going to get ugly real fast. The first one, there's 3 whites and 1, 2, 3, 4, 5 blacks. And then off of that, if the first one was a white, then I have 2 whites left and 5 blacks left. So over here, off of this one, I'd have 2 whites and 5 blacks. Off of, and are you guys getting the picture? How ugly this would be? This one, I have 2 whites and 5 blacks. And off of this black, I'd have 3 whites and 4 blacks. And are you guys all right if I run out of steam and stop? Can you picture how the rest of this would follow?
Yeah.
And do you see how it would end up giving me the same results, but I would end up having 56 branches on this tree, which I think would be a little bit cumbersome to draw. But a possibility tree would show all 56 things as separate branches, as opposed to the probability tree where we're labeling them with their probability. Difference between the two a little bit clearer.
Yeah.
And so that kind of is a lot of what's from that first section and a little bit what's from the second section of the textbook. They start right away looking at probability. When I teach these concepts in any other class, before I look at probability, I look at counting, but we're doing it the opposite way so that we can kind of coincide with your textbook. So now they introduce this idea of counting. And the counting principle says that if one event can occur. Oh crap, guys, yell at me. It's 11:55, isn't it? We should have stopped by now. I just looked at the clock. I was having so much fun, I lost track of time. I'm so sorry. I'm gonna stop recording and